Let's build a linear regression model in Python so you can better understand how it works. You can think of linear regression as the baseline method of machine learning that turns a chaotic dataset into a simple line, so let's break it down. Imagine you run a small lemonade stand every Saturday and you keep noticing the same stressful thing. Sometimes you make a ton of money and other times you barely break even, so your business feels like the universe flipping a coin on you. So you decide to stop guessing and start treating it like a problem you can actually measure. The next week you get a diary, and every Saturday you start writing down one simple thing that you suspect matters a lot, which is the temperature outside. So you take note of how many degrees it is outside and also how many cups you've sold. After a few weeks, you've accumulated a tiny data set that looks something like this one. And now you're staring at the pattern thinking there has to be some relationship, and there is. Linear regression gives you a basic rule or formula that turns the temperature outside into the expected number of cups of lemonade you'll sell. And it chooses that rule in a way that's useful but also as simple as possible. The simplest possible way to model data is with a line, because a line's slope has a very clear meaning. It tells you that every time the temperature outside increases by 1 degree, your sales tend to go up or down by a certain amount. So what makes up this line in plain terms? Essentially, it has two knobs that you can adjust. The first knob is the baseline or y-intercept, which is what you'd expect when the input is 0. The second line is the slope, which tells you how steep the line is and also gives you insight into the amount of cups you'll sell for every extra degree. If the slope is 2, then going from 70 degrees to 75 degrees increases your sales by about 10 cups. And this slope is the whole learning part of the linear regression machine learning method, because it's the number that captures how strongly your outcome changes when the input changes. Now, here's the key. Your diary points will never line up perfectly on a singular line because real life has noise. Some Saturdays there's a sports game nearby and you sell more cups than usual, but other Saturdays there's a thunderstorm that scares everyone off, and other Saturdays you run out of ice. That noise means there will never be one perfect line that hits every single data point, so linear regression defines the best line in a very specific way. After trying so many different potential lines, it chooses the line that misses the points as little as possible. Now, what do I mean by this? Model looks at a data point and compares what your model predicted to what actually happened in reality. That difference is called an error. If your model predicted you'd sell 80 cups and you actually sold 90, then your error is plus 10 cups. If you predicted 80 but sold 65, then the error is negative 15 cups. It takes those errors for every single data point and squares them. This is so negative and positive errors don't cancel out, and also so that big errors hurt more than small ones. Finally, it adds all these errors up across the entire data set. The best line is the one that makes this total squared error as little as possible, and this is called minimizing error. When you fit a linear regression model, you are basically letting the model choose these two knobs, the baseline and the slope, so the line threads through your messy cloud of data points in the most defensible way. Once the line is fit and these two knobs are frozen, you can use it for real-world situations, which is the practical payoff. Next Saturday's forecast says 88 degrees Fahrenheit and you want to know how many lemons to buy, so you plug in 88 and get a predicted sales number. But there's another payoff that's just as important, and that is interpretation. The slope of the line becomes a sort of story. Like in our data, every extra degree of temperature is associated with about 2 more cups sold. Now we have to extend the story slightly because real-world problems usually have more than one factor. You know that the temperature outside matters, but realize that the day of the month might also matter if you put up a bright sign and also if you've upped the prices. This type of linear regression is the exact same idea, except instead of one input, you have several, and the model learns a different weight for each one. There are multiple factors contributing to those two knobs of the baseline and slope. In the lemonade stand analogy, it's like you're building a recipe for predicted sales. Start with a baseline, add something for the temperature, add something for foot traffic, subtract if it's raining outside, and the model learns the size of each of these adjustments from the data. And the linear part means all of these effects are added into one singular line. And that brings us to the real life point. Why use linear regression at all when the entire world is so complicated? Well, you might use it because it is the cleanest first tool you can use to both predict with and explain. It's fast, it's interpretable, it gives you the opportunity to think about inputs and outcomes, and most importantly, it gives you a baseline to beat in the future. All in all, it's the best way to start getting ready for more advanced machine learning. So if you were to do this in real life with your own project, your steps would look like this. You'd pick a problem you care about and find a dataset for it. Then you'd pick an outcome, which is something you care about. amount. In our case, it was the amount of cups of lemonade we sold. Then you'd fit a linear regression line that minimizes these total squared mistakes. You'd interpret the slope as how much the outcome changes when the input changes by a certain amount, and you'd also use the model to predict and plan. And if you'd like to see my example coded out for you in Python, then don't forget to follow so that you don't miss part 2. See you then.